During this course, we are going to discuss different type integrable systems at quantum level. And in order to, most of them can be subdivided into large classes. Many body systems, and spin type systems. Spin systems, I mean some spin chains, Gaden models, and so on. We begin with this type models because main topic of our course is the so-called beta-ansatz method, and it is very widely used in this type models. But in order to discuss quantum models, we need to introduce some notations and some notions underlying integrability. And this is why we begin, maybe this lecture and maybe next one, but 1 or 2 lectures will be devoted to classical integrability. Because the objects we are going to discuss at quantum level are quantum versions of classical constructions. So for today, our topic is some kind of introduction or an overview of classical integrable systems. But I should say that most of objects I'm going to introduce and most of constructions I'm going to describe here will be directly generalized to quantum level. So it is important to understand classical integrability, main constructions, main statements. First of all, when we move to quantum level, we quantize something. What we quantize? We quantize classical mechanics. Classical mechanics is given by several objects. Is defined by several objects. Classical mechanics. I mean classical Hamiltonian mechanics, because all models we are going to discuss here are Hamiltonian models. So at the level of classical mechanics, we deal with some phase space, which is given by some manifold, and this manifold should be Poisson. So that there is a Poisson bracket on it. And it is important, of course, to have Poisson brackets. We'll give some examples just in a few minutes. And finally, we need to define the Hamiltonian function. So it's some smooth function on this phase space. And at quantum level, yes, and so having all these objects, the Hamiltonian equations of motion, the dynamics, is defined as F dot equals to Poisson bracket of Hamiltonian with some given function f. So where f is a function on the phase space. it can be coordinates on the phase space. For example, when you discuss many-body systems, you have n particles. Each particle has momenta and position coordinate. And traditionally, for many-body systems, we define the so-called canonical Poisson structure. In this case, this Poisson bracket has very simple form. It is just derivative of f with respect to pi and minus vice versa. So we always think about, even at the moment when we discuss classical mechanics, we always think of how it should be quantized. So at quantum level, we'll see that the functions on the phase space are quantized to some operators. I won't go during this course into a general problem of quantization. We'll use some very concrete and very general recipe, which assumes that some function on the phase space at quantum level is replaced by an operator which acts on some Gilbert space. So it is an operator on a Gilbert space of states of quantum model. And the quantum model can be considered as generalization of classical mechanics in the sense that it has some parameter called Planck constant, and when you consider a limit of the Planck constant, when Planck constant is go to 0, then you should reproduce somehow classical mechanics. So this is just a very general idea of quantization without any details. Okay, so what is integrable system? This is what I just wrote here. Is valid for any Hamiltonian system, but we are going to discuss integrable systems. Integrability at classical level implies the so-called Liouville theorem. So the model is integrable. The model with say, of n particles is integrable if there exists n integrals of motion, n independent integrals of motion or conservation laws in involution with respect to some given Poisson structure. For example, if we have a canonical Poisson structures, then we use this one. And the statement says that the model is integrable if we have a number of conservation laws such that the Poisson bracket between them is equal to 0. Then it means that the corresponding Hamiltonian floors commute with each other the Hamiltonian flows generated by these functions, which are conservation laws. So that in fact you may, when we write here a dot, we assume a derivative with respect to some time variable. And this equation can be written as derivative of ik with respect to some ti. So where ti is a dynamics generated by Hamiltonian, by this Hamiltonian. And the Liouville theorem says that the model is integrable if all conservation laws are in involution. And it means that you may choose any floor generated by any conservation laws, by any conservation law, and then the rest of conservation laws will be indeed conserved with respect to dynamics in any time. And at quantum level, yes, there is also a widely known relation between classical and quantum mechanics, which says that the Poisson bracket between two functions is equal to the limit of commutator of operators divided by Planck constant. So it is natural, so the commutator of operators at quantum level, if you consider this limit, give you Poisson bracket. It means that at quantum level, we are looking for operators which commute with each other as operators acting on some Hilbert space. And in what follows, we will define some constructions. We will consider, in fact, several constructions, and there are a lot of them, which gives you somehow a set of commuting operators. And these operators can be quite complicated. They can be differential operators or difference operators or just operators given in terms of some generators of quantum algebra, and then you may then you can study representations of this quantum algebra, and this is the way how you may define your your Hilbert space. But this is what we are going to discuss next, and now we are doing with classical mechanics. So we are coming back to this definition, and let us what does it mean? It means the following. Suppose we may write equations of motion in matrix form. So we have some dynamical system, Hamiltonian. For example, if we consider some interacting particles, then we have a set of equations like and so on. Yes, we may just write explicitly Hamiltonian equations of motion. In canonical, in the case of canonical Poisson bracket, they have the form, and so you just need to choose the Hamiltonian function, and then write down 2n equations of motion. Suppose now that all these equations can be written in matrix form. So we have two matrices, a pair of matrices. In some examples, let the size of matrices be n. But it is not necessary, in fact, that this n should coincide with the number of particles or something like that. There are different Lax representations. But just for simplicity and just to begin with, let us think that the size of matrix exactly corresponds to a number of degrees of freedom. And suppose that equations of motion are written in the following form. L dot is equal to commutator of L and M, where L and M are matrix valued functions on the phase space. Then, from this equation, it follows that we have a number of conserved quantities. For example, let us write them as follows. Where k goes from 1 to infinity. And it is easy to see why we have these conserved quantities. It happens by the following reason. Consider first, let us call them not I, but H. So these are Hamiltonians, in fact. We generate dynamics. And we call the time variable corresponding to these dynamics Tk. First, let us verify the statement for k equals 1. Then we should compute trace of both sides of equation, and we see that the time derivative with respect to trace of matrix L is equal to trace of commutator. And using the property of trace that you may permute matrices under cyclic permutation, then you get 0 here. Next case is k equals 2. Now we have 1/2 trace time derivative of trace of L squared. And then we just apply Leibniz rule, yes, because just if you have some product, and then the derivative of a product of matrices is just A dot B plus AB dot. And so we compute it here. We have trace of L dot L plus L dot. We again can move this L here or this L here. So as a result, we obtain trace of L dot L. And finally, we substitute here the right-hand side of the Lax equation. It gives you commutator L and M, here L. Okay, let me write it here. So we have trace of L, M, L minus M, L squared. And you again move this L to the left and obtain 0. Or not this L to the right, just to be the same. And you can show easily that the same construction works for any k. You may prove it by induction or as you wish. So we have a number of conserved quantities. They are, in principle, they are not independent, but you may just, in any example, you may and you should verify what number of integrals of motion is independent. Let me show you example of classical integrable system, many-body system, which is called Kalodzer-Moser model. And this model at quantum level will be discussed in the second part of our course. But when talking about classical integrable systems, it is a very illustrative example. And this is why let me begin with it. So Kalodzer-Moser model. It is the model which is given by the following Hamiltonian function. So it's a model of one-dimensional particles. You may think of particles moving on a real line or on a complex plane. Both variants are possible. So we have a kinetic energy plus, but I put here minus, I will explain why. Plus interaction described by inverse square potential. In fact, it is easy to discuss the complex integrable systems when all variables are complex. And this nu is a coupling constant. So Qi are positions of particles, Pi are momenta. And this is a non-trivial dynamical system with a nonlinear interaction. And it appears that this model has a lot of symmetries, has a lot of different applications, and it can be even solved exactly by some nice methods like projection method. So a lot of good properties for these models are known, for this type models are known. And of course, it has Lax representation. Just let me write it how it looks like for you to understand nature of the objects we are discussing. So this L can be, let me write it here. Matrix elements of this matrix, it is a matrix n by n, where n coincides with the number of particles. N by n matrix. And it is given by the following expression. So when writing like this, we have a delta symbol here, Kronecker delta symbol. It means that these momenta are arranged on the diagonal. And these expressions are off diagonal, because when it equals 1 when I is not equal to j. So here we have mu over qi minus qj. So this is the structure of this matrix. And M matrix, in fact, is has a very similar structure. M matrix has some elements on the diagonal, and it has the following expressions for off-diagonal elements. And this di is equal to this sum. So this is just explicit expression, and you may verify. So you may verify that the Lax equation generates equations of motion. In fact, we have here n squared scalar equations, yes, because matrix is n by n. And what happens is that on the diagonal, for the diagonal elements, you will have exactly equations of motion. And off-diagonal elements for this equation will turn into some identity, which is always true.
In the equation of motion, the h will be like
Sorry? Yes, VH is this one, yes. Equations of motion generated by this Hamiltonian. And maybe it is better even to write here, maybe it is even better to write here from the very beginning qi dot. So it's just a velocity. In fact, we may write it in different ways, but for just concretely for this model, velocities are equal to momenta. Okay, now we have a set of conservation laws here, which follow from this Lax equation, and they are given by traces of powers of matrix L.
You have written n squared next to this equation of Lax sphere.
Sorry?
You have written n squared there. What does it imply? Is like n by n metric, or there are n squared such equations?
No, it means that L and M are matrices n by n. Yes, so you have n just ordinary scalar equations. Yes, n squared. Where ij goes from 1 to n. So, and my comment was about that you see in Hamiltonian mechanics or Lagrangian formulation, you have only n, or in Hamiltonian case 2n equations. And here we have n squared equations. So there is we have larger number of equations in this example. And so we should explain why we have so a lot of equations and how it works. And I just told you that equations of motion are reproduced from the diagonal part. And off-diagonal part is cancelled out automatically. Okay, now, so it is an exercise just to verify that it works. But what we need in integrable systems is not just a pair of matrices. This equation doesn't know about this important property, which the main property of the Liouville theorem, which says that the integrals of motion should be in involution. Moreover, this equation even doesn't know about any Hamiltonian structure. So if we write, this is what I did just 1 minute ago, I changed momenta into velocities. So you may consider it just like some form of equations which don't know about any Hamiltonian structure. And if you want to apply Liouville theorem, we of course need some Poisson structure, and then we need to prove somehow this involution property. And in order to define in order to prove this statement, so the statement is in fact that if you put here not velocities but momentas, and if you compute all these Hamiltonians, H1, H2, and so on, up to Hn, then all of them are independent and all of them are in involution. The reason is the following. There exists the so-called classical R-matrix structure, which guarantees you this involution property. Let me explain what it is. Now we should introduce some notations which are widely used both in classical and quantum integrable systems. We denote L1 as a component of a tensor product, L multiplied by 1, by identity matrix of size n by n. And L2 be identity matrix multiplied by L.
So your L is that matrix?
For this model, this matrix, for this model it is. So maybe I should recall you some notations related to tensor products. So if you have a pair of matrices, in fact they can be of course rectangular, but it is maybe easier to deal with square matrices because our matrices here are square matrices. So just if you have a pair of matrices n by n, then what is the tensor product of A and B? It is a matrix of size n squared by n squared, and it can be presented in the block matrix form. So you just put here A11, element of the matrix A, multiplied by the total matrix B. Then A12 by total matrix B, and so on. And each block is constructed in the same way. So this is n, 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 n. So totally we have n squared by n squared. Yes. With this definition, we have some nice properties. For example, if you multiply tensor products then the multiplication rule is very simple. You just multiply A by C all times B, D. Yes, so you just act in some certain tensor component. And for example, and the same is valid for action on the tensor product of vectors. For example, if you have a tensor product of two matrices, and it may act on a tensor product of two vectors, and the result is given by application of A to U multiplied by application of B to V. It is very easy to see it from this definition. I mean, for example, this property just follows from, because if you put here another matrix which is C over D, then it is just C11D, C12D, C21D, and so on. And for example, let us look at, and now we compute the product. And let us compute what happens in this block 1, 1. In this block 1, 1, we have a product of this column by this row. Yes, so this row by this column. And what we have here, A11B multiplied by C11D plus A12B, C21D, plus and so on. And obviously it is equal to the sum over k from 1 to n, A1k, CK1, multiplied by BD. And this is exactly AC11, as it should be. Yes, because what we should, according to this rule, we should obtain here AC11 multiplied by BD. This is exactly what we have. So just a simple way to verify some properties, but all of them are quite simple. Okay, now,
Supposing to UV vector power.
yes, U and V are vectors here, yes. We will discuss more examples on the property of tensor products during this lecture, because it is important for us at quantum level as well. Okay, now what is the statement about classical R matrix which will provide us involution property? Let by definition, no, I should just let me also introduce notation which I'm going to use during this course. This is a standard basis in matrices n by n. Standard basis in matrices n by n. It means that this is a matrix which has 1 at position ij and zeros at all other positions. So that the matrix elements for this matrix is given by the product of delta samples. Okay, now so any matrix A is written like Eij, Aij. Yes? This is just the definition of matrix elements. So now if we deal with the tensor product of matrix spaces, for example, with the square of matrix space, then the basis in matrices in the second tensor power are given by, basis is given by this set of all possible products. Yes, so it is numerated now by 4 indices, and this is why it is n squared by n squared. So multiplying all these unit matrices, you will obtain all possible matrices n squared by n squared with a single element which is equal to 1, and all others are equal to 0. So any element of, then any element from this space can be written in such a general form, some Rijkl multiplied by these basis elements. And I put here 1, 2, assuming that 1 is just this space, the first tensor component, and 2 is the second tensor component. So when I will also use notation where if I write some object from the space like this, then I will also need I will also sometimes write R21, meaning that I change the components, tensor components. So that R21, from this definition of R12, R21 is equal to Rij KL EKL Eij. And the sum is overall indices. So, now let us come back to what I promised to explain. So our matrix elements of our matrix L of the Lax matrix are some functions on the phase space. Yes. So, for example, diagonal element is given just by a coordinate, which is momenta, and of diagonal elements are some functions of coordinates. And we may, of course, define a set of Poisson brackets between all possible matrix elements. And there are, so we have n square here and n square here. So we have n in the fourth power of such brackets. Let us, by definition, say that L or this is just a notation. This is just a notation, but this notation by definition means the following thing. So we put here all possible Poisson brackets between all possible matrix elements and multiply them by these basis matrices from the second tensor power of matrix space. So we just arrange all possible Poisson brackets in this large matrix. Now, what is the statement? Suppose, let us formulate it like statement. Suppose there exists element of second tensor power of matrices, some such that this object L1, L2 is represented in the commutator form. More explicitly, it should be represented like L1 commutator with R12 minus L2 commutator with R21. Then HK and HM are involution, where HK are defined as we know from Lax representation. So this is a very important statement in theory of integrable systems. So it's not enough to to construct just Lax representation. Although, of course, if you have it, in fact, you are almost happy, because to have Lax representation is also looks like a miracle every time. Of course, you cannot construct Lax representation for any system just by hands. You should you should know some additional arguments, some arguments from some symmetries or some group theoretical constructions of how this Lax representation may appear. But even if you have this Lax representation, it's not enough for you to conclude that the model is Liouville integrable. For the Liouville integrability, you need to prove this involution property, and this involution property follows from existence of classical R matrix. So this object is called classical R matrix. Classical R matrix. This equation is called classical R matrix structure. And this relation can be considered as sufficient condition for Liouville integrability. It's not necessary, in fact, but it is sufficient condition. Okay. Yes, and why it is important for us, why we are discussing details of classical integrable systems at this level. This is just because at quantum level we are going to deal with quantum analogous of all these objects. We'll have quantum Lax operator instead of classical Lax matrix, and we'll have quantum R matrix instead of classical R matrix. So the quantization of this model can be considered as quantization of this Poisson structure. Let me just repeat you again that if we write just only the Lax equation, we have we even have no Hamiltonian structure. Yes, and so the Hamiltonian structure appears and the Poisson structure appears from this relation. Okay, now we know something. Yes, and of course for this model I told you about for the Kalodzer-Moser model. Of course, our matrix exists, and you may write it explicitly. I'm afraid to make a mistake, but it should be something like this. And here we have IJ, EJJ. So this is an example of concrete R matrix. Yes, and also
This is R matrix or L?
This is R matrix. This is R small 1, 2. So it's an object from the second tensor power of matrix space. Just
Could you please give a general definition of the R matrix?
this is a definition. If there exists such element from this space.
So it works for any integrable system?
Yes, it works for any integrable systems. But of course, So in fact, R matrix is a more fundamental object than, for example, Lax matrix or Lax pair. You see that existence of R matrix guarantees integrability. And of course, when people understood that R matrix is so important, they tried to find what kind of R matrices do we have. And in order to answer this question, the most natural way is to write down some equation for this R matrix. And equation for R matrix equation for R matrix follows from Jacobi identity for Poisson bracket. So the Jacobi identity how much time? Jacobi identity says that if you have a Poisson bracket, then it satisfies the following relation. So, and if we write down Poisson brackets in terms of some object which we call classical R matrix, then this equation applied to matrix elements of Lax matrix should provide you some restriction to R matrix. So if you write down Lij, L, and Poisson brackets, also Poisson bracket with LMN plus cyclic permutation, then it should mean something. It should impose some restrictions on these coefficients. Yes? And the easiest way to see it is just to use our notations. But now, you see, we have three matrix elements of L. We had here two of them, but now we have three. So it is natural to multiply this equation by Eij times EKL times EMN. So now we deal with the object which is a element of tensor cube. So what I am saying is that the Jacobi identity can be written like this: L1, L2 with L3 plus L3, L1, L2 plus L2, L3, L1 is equal to 0. When now L1 is L times 1 times 1, L2 is 1 times L times 1, and L3 is 1 times 1 times L. Now you may, it is also some exercise to do. I'm not going to write it in details. You may look at some of my lectures on classical integrable systems, or look at some books. So this is a very general topic, in fact. And it can be it can be seen that the sufficient condition for this Jacobi identity to be true, yes. Maybe I made a mistake. I told you that this is sufficient condition for Liouville integrability, but not necessary. Of course, it is sufficient and necessary condition. But this equation, this Jacobi identity, is a sufficient condition for the classical Yang-Baxter equation for the classical Yang-Baxter equation. Let me write this classical Yang-Baxter equation for in some special case when our matrix is skew-symmetric. Skew-symmetry means that R12 is equal to minus R21. Then you have this relation plus maybe plus something. Plus something which I denote like star, and it means that there are some modifications of classical Yang-Baxter equations. There are some what is called the modified classical Yang-Baxter equation, there are dynamical Yang-Baxter equations, and so on. So there are some additional terms, maybe. But so the most simple and the most clear form for Yang-Baxter equation consists of these three terms. And this is a relation which defines you this classical R matrix. So you may find solution to this. You may try to find solution to this equation, and then you know that if you just find solution to this equation, then you have some integrable system.
Sorry, I don't quite understand. From this equation, Lij, the Jacobi identity of Lij, Lk, Ln, we go to L1, L2, L3.
You see, we multiply. So this equation includes 6 indices. Yes. We multiply all of them by the corresponding tensor product of matrices, and sum up overall 6 indices. For example, like we did here. For example, when we write Lij, Lkl, we multiply them by tensor product of 2 matrices and sum up overall indices. And we denote it like L1, L2. And now when we have when we have objects so which are cubic in L's, yes, we have L1, L2, and L3. Is it now clear or not?
So you mean this equation and that equation are the same thing?
Yes, this is the same thing, yes. So so we should put them for any I, J, K, L, M, N.
Sorry, but where we connect like L and R?
Sorry, say it again.
Where we connect like the L and the R matrix? Where are they related? Only there?
Yes, they are related like this. So originally, we said that our involution property, which we wish to have, and which is the main part of a definition of integrable system, this property of Liouville integrability follows from existence of this R matrix. So if you find such an object which provides you this relation, then these quantities, these conservation laws are in involution. So, you may think at the moment, at least at the moment, you may think about it like about miracle, because no one guarantees that you will find it. But if you find somehow such an object, then you obtain the main property of integrability. But now we understand that our matrix is very strong and very fundamental object. And of course, it is important for us to understand what kind of our matrices exist. So, and we want to write down some equation which defines our matrix. And this equation naturally follows from Jacobi identity. So we write Jacobi identity, and then I skipped here some details, but if you substitute here what is written over there, then you will obtain some expression which consists of L and R, and then again compute. So for example, you will have here L1, R12 minus R12, L1, and so on, and then compute again the bracket of L1 with L3, yes, and use it again. But when you have L1 and L3, you should put just here L1, L3, L1, R13, L3, R31, yes? So you substitute.
Sorry, the consequence of doing this implies the Young-Baxter equation, but not the existence of the R matrix. It's in case the R matrix exists and the
yes, if our matrix exists, then it should satisfy this equation. It is a sufficient condition for this Jacobi identity.
But if we just have Jacobi identity, we cannot get the R matrix if we don't know if it exists.
No, we cannot. There is no way. We just so our logic is the following. Suppose our matrix exists, there exists such a matrix which satisfies this relation. Then this is what we want. This is just a victory, and our model is really integrable. So then we understand that this is an important object, and we just try to write some equation which defines it.
Sorry. Actually, I'm confused. If you substitute this to that equation,
Mm-hmm.
and you see you will get this
Mm-hmm.
this equation.
Yes. So in fact, plus something. I didn't write what this is a star, which may include, for example, if our matrix depends on dynamical variables, then you may have non-trivial brackets between R and L. For example, they are here. So if you have these terms, this equation is called dynamical Young-Baxter equation. And sometimes you may put not zero here, but some element. In fact, if you write it explicitly, then what you will have some commutator of some expression, this right-hand side of this equation, maybe plus these dynamical terms of this type, maybe plus something, commutator with L1 plus L2 plus L3. And in fact, and this should be equal to 0. And then you say that sufficient condition to fulfill this Jacobi identity is to require that all this expression is 0. It is sufficient, but not necessary.
So this expression is this one?
Yes, is this one, yes.
And if we get an object that satisfies Young-Baxter equation, we can go get the integrability?
Yes, yes. So it means that there is some integrable system or family of integrable system which is described by this R matrix. Yes. So R matrix is a very fundamental object. Let me say you also that if you have R matrix, then you may define these M matrices. We had Lax equation. Where K is numerates the time variables which correspond to different choices of Hamiltonians from 1 to Hn. you may choose any conservation law and choose it as Hamiltonian, and and write down dynamics with respect to this Hamiltonian. This will correspond to some time tk, and then you have, for each time, you have Lax equation, and this mk can be defined as, maybe with minus, I don't remember the sign, but main formula is like this. So what does it mean? Let me also explain it. Maybe I should, we don't need this anymore. What does it mean? So you just, how to compute this? This is a trace over the second tensor component, yes? So what does it mean? For example, if we have this R12, or okay, it is written here. How to compute the trace over the second tensor component of R12 with some matrix A2. What is A2? A2 is 1 by A. So if we multiply R12 by A2, then what happens? It is equal to Rij KL Eij times this A2 is 1 over A, yes? So it is multiplied by the second component, AKL A. And now we compute the trace. And when you compute a trace of some matrix with any matrix unit, with element from basis, it is of course equal to ALK. Because if you put here some all possible Eij, then this G should be equal to K and I should be equal to L in order not to obtain 0. Yes? Is it clear? Okay. So if we compute here the trace over the second component, of this expression, then what we get? We get a matrix which belongs not to second tensor power of matrix space, but just to ordinary matrix space. Yes, it is now just an element of this matrix, original matrix space, and it is given by Rijkl Eij A LK. And this is what we mean here. So the statement is that if you have classical R matrix and if you know also L matrix, Lax matrix, then you may define these M matrices just by this rule. And in fact, it is quite simple statement. You just need to compute. You just use this relation. You just use this relation, and then you may compute L1, L2 in some power k using Leibniz rule, and then take a trace over the second tensor component. So here you will have some large expression, because when you make this calculation, you use Leibniz rule k times. So you will have a lot of terms, but all of them can be combined into some commutators. And after taking trace, many of them just vanish, and some of them appear into commutator with this matrix. So it's also another exercise to do, but the statement is that if you have classical R matrix, then you know a lot about your model.
Excuse me. What was the purpose? It was to show what is the aim in this process? To get M? Or?
Yes, it's a. I'm explaining that if you know R matrix and L matrix, then you know M matrix as well. Because there are different constructions how to define and how to find sometimes the Lax matrix. But even if you have some candidate for the Lax matrix, you can't be sure that you will find a matrix which gives you correct equations. And what I'm saying right now is that if you have classical R matrix, then there is no problem. So M can be found easily. Just the K object is classical R matrix. Okay, now, yes, and this is also important for us because at quantum level we will discuss, roughly speaking, two large classes of integrable systems. One of them consists of many body systems, and this is, for example, the Calogero-Moser model and its different generalizations, which we will discuss. Another class of models is given by the so-called spin models, for example, spin chains or Godin models or integrable tops. These type models, both spin chains and integrable tops, use different Poisson structure. So if in many body systems we usually use canonical Poisson structure between momenta and coordinates of particles, then in top-like models or spin-like models at classical level, we use linear Poisson structure. Linear Poisson or Lie-Poisson structure. Okay, Poisson-Lie structure. How it appears? It comes from, it naturally comes from the algebra. For example, general construction says the following. If you have some Lie algebra, so it's a vector space with generators, with some generators, yes, and operation which is called commutator, which is very similar to definition of Poisson bracket, because this commutator as well as Poisson bracket should be skew symmetric and satisfy Jacobi identity. So the definition of commutator in the algebra is exactly the same the definition of Poisson bracket. So, if we have some Lie algebra, then its commutator should belong again to this vector space. It's just by definition of commutator. So if we define some operation on the vector space, it means that the result of this operation gives you another element of this vector space. So let us write it in the general form as follows. It is some ABC. It is some, okay, maybe not C. Let it be alpha, beta, gamma, and here C, like this. This is what is called structure constants. By definition, as I told you just, this commutator should satisfy Jacobi identity. So the statement, what I'm which I'm going to use now, is that if you have any Lie algebra, with some given commutator. Then you may construct Poisson brackets by the following rule. So this is a Lie algebra, say G, with generators TA. Then on Lie coalgebra, so on the dual space, we have a Poisson brackets of the same form. And the Jacobi identity for Poisson brackets follows from Jacobi identity for commutators in Lie algebra. This Jacobi identity gives you Jacobi identity here. So it's a very simple but very important fact. And this is what we are going to use. For example, in SU2 Lie algebra, we have the following commutation relations. Sigma 1 and sigma 2. Commutator is equal to 2i sigma 3. And so on. Okay, let me write it like so. This is the relation for SU2 Lie algebra. This is a set of relations. Or we may just write it like sigma alpha sigma beta is equal to 2i epsilon alpha beta gamma sigma gamma. Yes. So this is a skew symmetric symbol. Yes. And we know that, for example, these relations are fulfilled by Pauli matrices. Also a very well-known fact. Sigma 1 is written like this, sigma 2 is like this, and sigma 3 is like this. Yes? And this, so here we should maybe put like heads, because this is just a definition of Lie algebra, but this concrete Pauli matrices satisfies the same relations. So the Pauli matrices provides you representation of this Lie algebra. Representation of Lie algebra in the space of matrices 2 by 2, which acts on the two-dimensional space. This is the so-called spin 1/2 representation. Okay, now, but in fact, we are not going to go into details of Lie algebras and representation theory here. This is just this is what I want to say, that if you have some commutation relations given by which define you some Lie algebra, then using these relations you may write down Poisson brackets. Let us write down Poisson brackets. So what the statement says. Let us write example. The statement says that if you have some definition of Lie algebra, then you may define in the same way Poisson brackets. So let us look at this definition of Lie algebra and write down Poisson brackets. X1. So our phase space is now three-dimensional. We have three generators here, and so we have three coordinates here when writing some Poisson brackets on some three-dimensional space. We should write it. We may write it like this, but in fact, this 2i is not important. We may multiply right-hand side by any constant, and the Jacobi identity will be valid again. So we just may put like, instead of 2i, we just write x3, then x2, x3 is equal to x1, and x3, x1 is equal to x2. And we know that this is indeed, so we cannot write anything we want in the right-hand side, yes, because Poisson brackets should satisfy Jacobi identity. And each Poisson structure is also some non-trivial object. But now, but in this example, we may be sure that the Jacobi identity holds true just because we use this very natural construction. We write this right-hand side according to these relations. Okay, now, yes, and for example, this bracket is used when you consider in mechanics, when you study Euler top. Yes, the Euler top is given by, the Hamiltonian of Euler top is given by quadratic Hamiltonian g1 x1 squared, g2 x2 squared, g3 x3 squared. If you write equations of motion for this vector x, which consists of 3 coordinates, then you will find that it is just Euler equation which describes your motion of three-dimensional rotation of rotational solid body in three-dimensional space. And these are just 3 components of momenta of this solid body. And these are components of inertia tensors, in principal axis. Or maybe it's better to say these are inverse components of diagonalized inertia tensor in principal axis. But these are just details. I mean that this is a very natural thing. It's not some kind of special exotic example. What we are going to discuss is the Poisson structures, which are related to some very natural objects like rotation of solid body and so on. Okay, and what we need now, we need to define linear Poisson structure corresponding to Lie algebra GLN. Lie algebra GLN, general linear, corresponding. This is the Lie algebra of Lie group GLN, which is a general linear group. Yes, so it is given by general linear transformations of n-dimensional vector space. So these are matrices n by n without any restrictions. Okay, then, so we may consider a commutator of.
No, the linear Poisson Lie structure is just this construction.
Yes, Poisson Lie or Lie-Poisson. I don't remember. Sometimes you may call like Poisson Lie or Lie-Poisson. Yes, this is exactly this construction. This construction means that if you have a Lie algebra, then you have a Poisson bracket on Lie coalgebra. Okay, now so.
But it seems like the same structure for this original Lie. Why we just not directly use this Lie algebra? What is the difference between this Lie algebra structure and the induced Poisson Lie?
So the difference is that this is an operation on vector space, Yes, Lie algebra is a vector space. And Poisson bracket is just Poisson structure. It's just an operation on the functions on the phase space. So they are similar but different.
Function here.
Sorry?
We can times some function here, but we cannot do this.
Of course, from this we can find how this bracket can be written for any arbitrary functions. Yes.
So this is different sense. Because here we don't have function.
So just there is no sense in definition of function of element of Lie algebra without saying something additional. For example, if you want to consider, say, universal enveloping of Lie algebra, then you may define some polynomial function of elements of Lie algebra or something. So you should say something additional in order to define it. But here, it's so I mean, we want to describe. We want to deal with variables which are similar to spin variables at quantum level. So at quantum level, spin variables are related to operators of this type, which are Pauli matrices with these commutation relations. And now we discuss what kind of classical variables, classical Hamiltonian mechanics corresponds to these quantum objects. And this it is given by Poisson-Lie structure. So it's just when we discussed canonical brackets, we had here delta symbol, so it's a constant. Yes, it's a constant function in the right-hand side, and here it is a linear function, linear function of coordinates. And there are also very interesting examples of quadratic Poisson structures. This is what we will discuss in what follows, but it is of course also interesting because they are related to Sklenin algebras and some classical analogs of quantum groups and so on. But now it is sufficient for us to consider linear Poisson structures. And what I want to say is that if we have, if we consider Lie algebra GLN given by commutation relations with these unit matrices, then we may construct again the Poisson structure related to these commutation relations. So let us just compute how what is the structure constant. So what is commutation? What kind of commutation relations do we have for this Lie algebra GLN in standard basis? This is a this is a matrix which has one only at place ij. So, and if you if you multiply them, you may verify that the result is given will be non-zero only if this j coincides with this k. And if it is not true, then you will obtain zero, just because you have one at jth place here, and you should multiply it by some column where one is at the kth place. So you have here delta symbol delta kj EIL. And we may write here this result, delta kj EIL, minus vice versa. In the same way, we may write this is a set of commutation relations. And according to our rule, which we just discussed, we know may define a set of Poisson brackets. Suppose we have some matrix which is going to be a matrix of dynamical variables. So it is a matrix with matrix elements Sij. Ij goes from 1 to n. And on this space, we may define Poisson structure in the following way. Sij skl is equal to delta il skj minus delta, no, sorry, vice versa. Delta kj sil minus delta il skj. And you may verify that it is indeed Poisson bracket by, you may straightforwardly verify Jacobi identity, or you may just say that it comes from commutator of Lie algebra GLN, and this is why it is true. This is a correct Poisson structure. So what time is it now? We should finish here, yes? Okay. So we discussed today the notion of Lax equations, the notion of classical R matrix, and next time we will discuss some more tensor notations and some very important examples like classical spin chains, which will be then quantized with the help of quantum analog of the classical R matrix, which is a quantum R matrix. And this is what we are going to discuss next time.